themes that we've been discussing this semester is how human population is going to impact our future in terms of getting resources, how that's going to affect the environment and the planet that we live on. So, as kind of background to that, especially talking about the extraction of resources of things that we use in our everyday products and for electricity, I want to talk a little about mining. And in order to talk about mining, we'll talk a little about minerals. And this is where we ended up last class, where we looked at the definition of a mineral, going back to the real basics here. It's a naturally occurring, inorganic, chemically homogeneous crystalline solid that has definitive physical properties. And it's these properties that we desire for the different products that we use in our everyday lives. A rock, again, is just an aggregate of one or more minerals. So just some useful properties, just to give you kind of a sense of what we dig this material out of the ground for. Different minerals, because of the way they're put together, the way they're bonded. Some minerals are more strongly bonded together than others. They end up having properties that we can use to make our lives easier, more rewarding. So, as we talked about before, some minerals are very, very hard, and we use that property. We use diamonds to cut other hard materials. But sometimes minerals can be ridiculously soft, and we use that property as well. Anybody know what the softest mineral is? It's talc. What do you use talc for?
Powders and makeups.
Powders, makeups, because one of its properties is it's soft. You don't want to rub your face with something hard and grindy unless you're trying to remove all of your skin. We talked about the use of cleavage yesterday. Cleavage and fracture refers to the manner in which a mineral breaks. I don't know if you've ever looked at table salt under a microscope. If you have, you know that it breaks into nice little cube shapes. The mineral calcite breaks into nice little rhombohedral shapes. The micas break into nice flat sheets. And we talked about how we can grind those up, throw them into paint. When you apply the paint, those little mineral grains, those flat sheets of mica will lie flat in relation to one another and give the paint some needed strength to keep it from blistering. Taste, some minerals have a distinct taste that we desire. Salt is the mineral halite, sodium chloride, one of the more common minerals on the surface of the earth. Some minerals have a characteristic feel. And if you've ever felt the mineral graphite, your pencil lead doesn't actually have any lead in it. It's a mixture of graphite and clay, and if you've ever felt that, you know how smooth and slippery it feels. And we use graphite as dry lubricants. Sometimes we add it to other lubricants, such as motor oil. There are lots of soft minerals. Talc is one of them. Talc has a characteristic softness that we desire, but it also has a feel that is different from a lot of other soft minerals. Most of the high-tech equipment that we use today is based on materials that we mine out of the ground. There's a mineral called tourmaline. It's a semi-precious stone, but it also is a natural polarizer. I don't know how many of you have polarized sunglasses. One thing that polarized sunglasses do is it filters out certain types of light. Polarized light, light that vibrates in one plane. Tourmaline is a mineral that can do this naturally and really do it at a high level, so it's a desired mineral in some high-tech optics. Some minerals are magnetic. Not surprisingly, the mineral magnetite is magnetic. Magnets are a mainstay in a lot of our modern technology. A lot of these are electromagnets. You can make a magnet by using wire and electricity, but some natural substances are just naturally magnetic. This is kind of an interesting one. I don't know who discovered this or how they discovered this, but it's a process called piezoelectricity. Just a fancy word for something that vibrates when you apply electric current to it. Not all materials do this, but some of our minerals do. And one mineral that does it especially well is quartz. When you apply an electrical current to quartz, it vibrates. It vibrates super rapidly. In fact, it vibrates at a set rate, somewhere around 100,000 times a second. So it's just bzzz, and it always vibrates at that rate. Now, a lot of you are wearing watches, and if you look closely at your watch face, you might see that it says quartz on it. Well, we use this property of quartz in watches, timepieces. Basically, all a quartz watch is a counter. We apply a current to a piece of quartz, and when it vibrates 100,000 times, a second is ticked off. And it's highly accurate. Now, I took a lot of time doing this next diagram, so I hope you appreciate it. So there's our quartz crystal. Out in nature, it has a little hexagonal shape. In your watch, it's super tiny. You'd have a hard time even finding it. And in order to make this little quartz crystal vibrate, you need to have an electricity source. That's why all your quartz watches have batteries. And then you simply run a current from your battery through the quartz. Now watch this, and then the quartz vibrates. Pretty good, huh? I bet I spent all of 5 minutes doing that. So really, again, it's just a property that we can use from minerals to give us something like a watch that's better than the last generation of watches in terms of its ability to keep precise time. That's just a very, very small partial list of useful properties that minerals exhibit. Again, I'll ask you this, I'll do this all semester. Look at the stuff around you. Look at your computer. Look at your 3-ring binder. Your pens. How much of that stuff was grown as a crop? Probably with stuff you got in class today, probably not much. The paper that some of you are writing on. If you're using a pencil, parts of your pencil that were grown. But everything else, look around this room, everything else in here was mined. So this is a big part of our everyday lives. And the part that you often don't see is the extraction part, the digging it out of the ground and then processing those raw materials into the goods that you see around you. Some of those costs you pay for, and some of them are externalized, as we talked about last class. Okay, how do minerals grow? The reason I talk about this is that it gives us some idea of where to find minerals. We know how they grow, we know what's required for their production, then we can go find these on Earth. And that's what one of the jobs that a geologist has. Well, most of the minerals on Earth are formed from the solidification of melted rock. Solidification of magma. These are what are called igneous deposits because rocks that formed from cooling magma are called igneous rocks. So minerals such as feldspars, olivine, quartz, micas, all these minerals are typically found in places on Earth where you've had magma in the past that's cooled into these different minerals. So geologists will look at areas that were once volcanic, or areas that were once buried deep, deep, deep within the earth. Both places are environments where magma can exist. Some minerals precipitate out of a water source. Maybe you did this as a little experiment in grade school or middle school where you took salt water. You can't really see the salt in the salt water. All you see is water. But when you boil it or evaporate it, that salt that was dissolved in the water is still there, and it precipitates out as mineral. And that happens naturally. You look at our great evaporating lakes, like the Great Salt Lake. The more water that evaporates, the more minerals that are left behind. The two most common minerals that you find from precipitating water is salt, halite, and another pretty common mineral which is called gypsum. Anybody know what we use gypsum for? Yeah.
Wallboard.
Wallboard. Why? You know why? Can't burn it, and it has a hard insulating quality to it, and it's cheap. It's really, really cheap because these deposits tend to form right on the Earth's surface. We don't have to dig down to get them. So it's an economically important mineral. If you've heard of the stone alabaster that some sculptors like to carve in, alabaster is gypsum. It's can be kind of a denser sort of mineral in terms of being able to hold shape, but it's really soft, so it's easy to carve. Secretion. So these are the shell fragments of living organisms. And it's responsible for an awful lot of mineral material on this earth. If you go into the oceans, a lot of what you find in the ocean bed simply remains of shell-bearing critters that inhabit the oceans. If you've heard of the rock limestone, limestone is one of the more common rocks that you find on the Earth's surface. It's really just a mixture of secreted inorganic shell fragments, fish crap, kind of the residue of the oceans that settle to the bottom. And the primary mineral that you find in secreted shell particles is one I'll talk about from time to time this semester called calcite. Calcites are the minerals that make up the rock limestone. And then a real minor way of forming minerals, for the most part this isn't economically important except in a few locations, are minerals that form from sublimation. Sublimation is a process where matter changes directly from gas to solid and solid back to gas. So you've got volcanic gases that come out and they immediately cool and make a solid. And a lot of the sulfur minerals are created this way. Sulfur is a mineral that does have some economic importance. It's pretty common. So you need an area where you can get a lot of it in one spot real cheap, and volcanic fumaroles, gas vents, are a good place to do that. Can you think of any other substance that sublimates? There's one really common one that you've probably used yourself. Something that goes directly from a solid to a gas to a solid. Dry ice, which is carbon dioxide. So they call it dry. It doesn't go through the liquid phase. Okay, some important minerals. You know, if you're really into geology, we have several thousand, I think somewhere around 5,000 different minerals. Different combinations of atoms and different arrangements, providing solids that have different properties. If you discover a mineral, you get to name it. Sometimes I know people have named it after themselves. I had a friend back in graduate school who discovered a mineral and he named it after himself, motite. His last name was Motes. But you've probably heard of most of these minerals. Feldspar, which is technically a group of minerals. These are the most abundant group of minerals that we have. Should say most abundant. In this case, we're talking about the Earth's crust, not in the whole Earth itself. I think the next mineral I'm going to talk about is the most abundant in the whole Earth. Feldspar is the most abundant in the crust. And it's got a few properties. It's hard, igneous. That word silicate, just go ahead and write that down. We'll talk about what that means in a minute. If you go out and pick up a rock outside, anywhere on Earth, it's most likely going to come from the family of silicates. It's our most important mineral group because most minerals out there are silicate based. So we're going to talk about that in a couple minutes. So just sort of store that in your notes and in your mind. Feldspars are a common mineral that we use in ceramics. I think when most people think of ceramics, they think of nice little flower pots and stuff. But we actually have some really high-tech ceramics that have different conductive properties. So ceramics are not just decorative pottery things. Clay minerals. You might not think of clay. You've all seen clay. Clays are actually a mineral. They're solid. But they have this amazing ability to hold on to water molecules. Do we use clays? Can you think of things that we use clays for? We actually use them a lot. We use it as a lubricant, drilling mud. All these oil and gas wells that are drilled, they use basically clay mud to help lubricate the drilling process. There's a wonderful clay mineral called bentonite. We'll talk about how clays form in another class or two, but basically you take some sort of volcanic material and you weather it on the Earth's surface, and these really hard minerals like the feldspars turn into clay. So they go from being really hard to really soft and really absorbent. Kitty litter. What do you want in a kitty litter? What properties?
You want it to suppress the smell of pee.
You want to suppress the smell, so we put additives in, but you also want whatever the cat goes in to absorb the liquid, right? That's what cat litter is. Bentonite is the primary mineral in cat litter. It's also the primary mineral in foundation. Makeup, that muddy sort of feel, it's super soft. That's the same thing. So cat litter and makeup foundation is essentially the same thing. Isn't that lovely? So clay minerals can be economically important. Quartz, you've heard of quartz. It's an abundant mineral. It's not the most abundant on the continents. That would be feldspar. But it's really abundant, and it's super resistant to weathering. So if you go to beaches around the world and look at the sand particles that you find on the beach, most of it's quartz. Because it's probably the most resistant mineral out in nature. It won't dissolve. You can stick in water for 1,000,000 years and it will not dissolve. And it doesn't break very easily also. It's a hard mineral. It doesn't have any planes of weakness, so it doesn't have cleavage. So it's like it's the last person standing in the weathering process. Everything else turns to clay, erodes away, dissolves, but not quartz. Quartz is about as resistant a mineral as you can get. Olivine. I mentioned olivine the last class. It's the mineral equivalent of the gemstone peridot, kind of lime green colored mineral. It's the most abundant mineral on Earth. because it's the most abundant mineral in the mantle. And the mantle is the biggest section of Earth by volume. I said a class period or two ago that I had a piece of mantle in my office. Well, that piece of mantle is actually a big glob of olivine crystals. Try to remember to bring some of this to class next week. You can take a look at what these things really look like. Calcite we talked about just a page ago in the notes. It's a really abundant mineral in terms of things that form in the ocean. So it's made out of shell fragments, fish poo. If you go out in the deep, deep ocean and look at the material that's at the bottom, it's going to have a lot of this stuff in it. And then when that ocean sediment gets more deeply buried and the water gets squished out of it and it heats up a little bit, it turns into the rock called calcite. Calcites are important on the continent because it's one of the rocks we look to for groundwater. They tend to be pretty permeable rocks, which means water can flow through them. As water flows through, it can dissolve some of the calcite, which makes it even easier for more water to flow through. So it can be an important rock if you buy a home. This is one of the rocks that you look for underneath your house if you have to drill a well. Mostly limestones and sandstones are what make what's called an aquifer, something we'll talk about later, which is a rock that contains a lot of groundwater, and it's good for drilling wells into. And then gypsum. We talked about this on the earlier page also. Like salt, it's a mineral that forms from ocean water that's evaporating. It's soft. It dissolves easy, but it's got good insulating qualities, and it does not catch fire, so we use this for wallboard. So again, lots of minerals. I've only put a half dozen to a dozen up here, but there are literally thousands of these things. If you want to learn about 20 or 30 of them, you can take physical geology, which is another introductory earth science course you might find interesting. If you really like that, then you can take mineralogy, and you might learn 200 to 300 of them. And even so, you're still only 1/20th of what really exists out there. All right, any questions so far? Okay, again, just a little background before we get into the human use of these things. And I think you'll find this kind of interesting. So up here, I have lots of rocks up here. Take a look at this rock right here. I can pass it around, but if you look at it, it's kind of got big pink minerals, got a couple dark minerals, it's got a few really light minerals. This is a form of granite. I think you've all heard of granite, right? Normal rock, right? What do you think is the most abundant element in here? You might not even have an idea of what to guess. What do you think? What's the most abundant element? Take a guess. Granite, okay. There's some quartz in it, but it's what I'm asking for, what are the atoms that make up the quartz and the feldspar and the different minerals in it? Silica, that's a good guess. What's that? Carbon. Carbon's a common element, right? You can guess all day, I bet you won't guess it. Oxygen. Oxygen. Does that look like it has oxygen in it? What do you think of, when you hear oxygen, what do you think of?
Air.
Air. But you know what? Our air only has about 20% oxygen. Almost 80% of it is nitrogen. Your body really doesn't use the nitrogen. Every breath you take in, 80% of it doesn't do anything. It just goes in, it goes back out. Your body's only interested in that 20% of each breath that has oxygen in it. This rock right here has almost 50% oxygen. This has more oxygen in it than in this whole room many times over. In fact, a little tiny piece of this would have more oxygen than what's in this room. Which is kind of neat because we need oxygen to survive, right? What about if we go to other planets? That's one thing we're concerned about is, oh, they don't have an atmosphere. No oxygen, right? Lots of oxygen. Go to the moon, go to the Mars. There's tons of oxygen there. It's just stuck in the rocks. But you can get gaseous oxygen out of this. You can take the oxygen that's bound up in these minerals and turn it into breathable oxygen. You have to add fluorine gas, which is highly flammable, highly explosive. So the process is really dangerous. I had a friend who worked on this project in graduate school, and when you do his experiments, they'd have to evacuate the building. You know, just as a safety precaution because it was that explosive. But it just goes to show that rocks themselves can be a source of material for things that you might not even think of. Something as basic as your breathable air can actually come from rock. So, in an average crustal rock, and remember, we talked about the Earth's crust, mantle, core, so we're just talking about the crust right now. The most abundant element is oxygen, followed by silicon. And as it turns out, those two elements really, really, really like each other. They bond together very easily. We'll talk about that bond and some of the minerals that those two elements can make in just a minute. Aluminum, third most common element in the Earth's crust. And I'll just sort of click up the rest of these: iron, calcium. So there's first five: oxygen, silicon, aluminum, iron, and calcium make up over 90% of all rock matter that you find in the Earth's crust. Pick up that rock right here, and over 90% of it is made of just those five elements. So in that sense, rocks are pretty simple. But it's that last column, all others. We have over 100 different elements: gold, silver, lead, platinum, antimony. I can go on and on and on and put up a periodic table of the elements, and you can look at all these different things. Those are also found in rock too, but in very minor abundances. And that's what geologists do. They basically go around looking for rocks that aren't typical. Rocks where you find some of those other elements in great abundance. You want to find gold, right? Well, there's probably some gold in this rock. Not enough to make it economically worthwhile to try to get out. So we look around for rocks that aren't like this. We look around for atypical rocks that have a lot of gold in it. And if you can find them, that's the basis of mining. Go to an area where these desired elements exist in great abundance, and it might be worth your time and effort and investment to dig them out of the ground and try to make money out of them. So that's what mining is. So the bottom line is that a lot of our usable earth materials have to come from unusual rocks. And that's one of the goals of geology, are to identify these rocks so that they can eventually be made into all that stuff that you buy and use and want. Okay, any questions so far? Again, we're sort of starting at the very basic and then kind of getting a gradually bigger and bigger picture here. Well, I said before there's 5,000 minerals, right? That's really difficult to deal with as a geologist. But one thing we can do is sort of subdivide those 5,000 into families and talk about them as groups. And these families or groups of minerals are put together based on commonalities, things that they have in common. Many minerals have similar properties that stem from chemistry that's somewhat familiar too. What is sodium chloride? Salt, mineral halite, NaCl. There's another mineral, KCl, potassium chloride. It actually tastes a little salty. You wouldn't like it, but you can taste it. But it has some properties that we desire. It's actually used in medicine. It's actually what they use to stop the hearts of patients who we lethally inject. So it has a huge effect on the body, a different effect than table salt. Table salt is actually something we need in our bodies. But they behave very similarly. And the most important group are the silicates. Silicates are any mineral that contain silicon, oxygen, and that word cations. How many of you have heard of the term cation? Probably heard of it. Well, just that we're all at the same place. Two terms that I want you to know, and you can make a little sidebar here. Cation and anion. Talk about anions in a minute. Cations are any positively charged atom. Anions are a negatively charged atom. So cations are positively charged, anions are negatively charged. If you have a hard time remembering it, I don't know. Some people are cat people, some people are dog people. I'm a cat person. Cats are positive. I had a girlfriend who tried to kill me once. Her name was Anne. Easy for me to remember. Okay, so cations and silicon and oxygen make up silicates. And this is something that I'm going to spend a little time on. We're not going to do much chemistry in here, but we're going to do chemistry of this one. And the reason is that silicates are the primary mineral that we find in lava and magma that come out of volcanoes. So when we talk about our volcano chapter, we're going to talk a lot about silicates. And then a little later we'll talk about weathering of rocks and minerals. And we'll talk about silicates. It's the most common mineral group out there. It's the most common mineral group on Earth. It's the most common mineral group on the Moon, Mars, Venus, all of our nearby planets. Most of the planet is made of this stuff. And the basic building block of all these different minerals is a little molecule, a little group of atoms called the silica tetrahedron. What's a tetrahedron? Hedron or shape, right?
Tetra as in four?
As in four. It's a four-sided pyramid-shaped molecule. And I'll show you a little diagram here in a mineral. And it consists of one silicon atom in the middle. And in nature, silicon atoms tend to exist as what are called +4 cations. It's basically just a little atom that has a +4 charge. I'm assuming you've all had a little bit of chemistry in your past, and you know that atoms can be positively charged, negatively charged, or neutral. Well, in nature, lots of atoms like to be charged. They like to be either a cation, a positively charged atom, or an anion, a negatively charged. In nature, silicons like to be +4. That's just the way they prefer to be. Oxygens out in nature tend to be -2 anions. And they love to bond together with silicon. They fit around silicon well. Because they have a -2 charge, they really dig that +4 charge of the silicon. So they're electrically attracted to one another. And 4 of these atoms fit nice and perfectly around the +4 silicon. And it makes a little molecule that is shaped like a tetrahedron. Again, I'll show you a diagram in the middle. So if you have a +4 silicon, okay, here's the +4 silicon. And you put a -2 oxygen here, and a -2 oxygen here, and a -2 oxygen here, and a -2 oxygen here. What's the overall charge on that whole molecule? Negative, how many? -4. And in nature, things don't like to have a net positive or net negative charge. If you're a -4 molecule, you're going to attract positive charges from the environment. And that's what happens with this little tetrahedron. It's sitting out there, it's negative, it wants to be around some positively charged things. So anytime something positively charged that comes nearby, they bond together. They're held together. And they form minerals that way. So it attracts cations, it attracts positively charged atoms. And the different combinations of cations and silica tetrahedron produce lots of different kinds of minerals with lots of different properties. So that's what a silica tetrahedron looks like if you're able to look at the individual atoms. It has this tiny little silicon in the middle, and then it has some big fat oxygen that surround it. The silicon in the middle is +4. Each oxygen around the outside is -2. So the overall charge on that little molecule is -4. So that's the little formula. 1 silicon, 4 oxygen with a -4 charge. So each of the atoms are noted on this little second diagram here. And it's not going to like being like that out in nature. It wants some positive charges around it. That's the shape. Okay, that's where the tetrahedron name comes from, that little molecule. Looks like it has a little 4-sided pyramid shape. And it'll track some positive charges out in nature. It's showing right here, iron. Iron is Fe. Out in nature, iron likes to be a +2 cation. So how many irons will fit around one of these tetrahedron? 2 of them. This is -4, +2, one more +2. You repeat that a million times and you have yourself a little mineral. And in fact, if you have 2 irons around a tetrahedron repeated a million times, you get that little green mineral called olivine. It's actually a very simple mineral chemically. The other thing that these tetrahedron do that you should know about is that they link together. They do something that chemists call polymerization. Have you guys all heard of polymers? It's just a fancy term for a molecule, like in this case, this tetrahedron, that like to bond with other tetrahedron. So they just keep linking together and they repeat themselves. You have tetrahedron bonded to tetrahedron, bonded to tetrahedron, bonded to tetrahedron. And that's just called a polymer, where you get a repeated series of molecules that bond together. The thing about these little four-sided pyramids is that they can make a whole bunch of different geometric shapes. They can form chains. So here's I'll just use that as a symbol for a four-sided pyramid. You got to kind of see this in 3 dimensions. And they can form together and make a chain of these that would repeat maybe 1,000,000 times. You can also form something like a sheet. That's a bad one. And you can repeat it in all directions 1,000,000 times. The other thing you should know is that when these tetrahedron bond together like this, the bonds that hold the tetrahedron together, let's say that bond right there, and that bond right there, that bond right there, they're super strong bonds. Really, really, really strong. Hard to break. You could repeat this out in this dimension too, and you can form what's called a big framework. Give you some examples here. I don't think this diagram is that great, but sometimes they're just sort of alone out in nature. They surround themselves by cations, and that repeats, but the tetrahedron don't bond together. In this case, the tetrahedron are bonded together as a chain. In this case, they're bonded together as a double chain. In this case, they're bonded together as a sheet. And I can't draw it in 3 dimensions, but you can imagine this being repeated in the 3rd dimension as well. And those are really, really strong bonds. So each of those different arrangements leads to minerals that have different properties. You guys have heard of the micas, right? A mica is a sheet silicate. The sheets themselves are really strong. The bonds that you find between each sheet are very weak. So it tends to break into strong sheets separated by bonds that aren't so strong. If you do this in 3 dimensions, where all of these tetrahedrons are bonded at every corner, what kind of mineral do you think you would have? What would be some of its properties? Those bonds are really strong, right?
It wouldn't dissolve easily.
Wouldn't dissolve easily, wouldn't break easily, right? What about melting easily? When bonds are really strong, how do you break them? You have to heat them up a lot. Lava and magma, it's really hot, right? That's one of the reasons why it's really hot. It has to be that hot to melt rock that has bonds that are this strong. So let's just go forward with this a little bit. A couple examples. Gave you this as the very first example where you have one tetrahedron. That's the part of the equation that corresponds to the tetrahedron, the SiO4, 1 silicon, 4 oxygen. Then you surround it by 2 iron, and that's called olivine. And you can see that the charges all balance out, right? You have a -4 tetrahedron. And again, this will probably be the most chemistry I'll give you all semester, is today. But it's something we'll talk about from time to time, so hopefully you'll get familiar with this. So again, this is just sort of showing each part of the chemical formula and what it corresponds to in terms of the atoms that are out there. So this is one thing I really want you to remember from this, because it's probably the most important chemistry aspect of this, is that the silicates, and remember your silicate is +4, right? And it doesn't want to be +4. It wants to balance out those charges. And it can do it in 2 ways. Okay, so let's review this and kind of build upon it. What's a silica tetrahedron? What atom is in the middle? So you have a silicon in the middle, right? What's the charge on the silicon itself? +4. The tetrahedron is surrounded by, that means that it's kind of going out to the back, by 4 oxygens, right? What's the charge on each oxygen? -2. -2, -2, -2. You combine all that and you get a -4, right? One way that this little guy can get his charge balances by putting cations around. Put an Fe, an iron +2 there. Fe +2 over here. You can put them anywhere. They just have to bond to it. +2, +2 balances out to -4, right? So this is Fe2SiO4. And the mineral is olivine. Got that part? Okay, I'm going to complicate it a little bit. Okay, that's the easiest way to understand how the charges get balanced out. The charge is always -4. Okay, so in this really simple case, you just attract +4. I could put different elements here. I could put magnesiums. Magnesiums are +2. So then I'd have Mg2SiO4. That's a different mineral. I could put calcium. Calciums are +2. I could put 2 of those there. I could put potassium. Potassium is +1. How many potassiums would I have to stick around this? 4 of them. Getting the point, right? One other way that silicates balance their charges and in the process give us different minerals is by polymerizing, something we just talked about a second ago. Polymerizing is when you bond these tetrahedron together. So there's your silicon. There's your oxygen. There's your oxygen. There's your oxygen. It's a 3-dimensional little structure. There's your oxygen going back. It's going to get repetitive, but what's the charge on the silicon? +4. Oxygen, -2, -2, -2, -2. Same thing we just had, right? You could put a couple of irons in here, each +2, it would be happy, right? You could put a couple magnesiums, each +2, it would be happy. You could put 4 potassiums that are +1, it would be happy. But in this case, I said what? It polymerizes, right? Which means that it will share these oxygens with the next molecule over. And I'll show you. So what you could do is you could put a silicon here. That silicon is +4, right? And you would have one oxygen there, one oxygen there, one oxygen there, and one oxygen there. We could do that here too, right? We could put a silicon over there, oxygen, oxygen, oxygen. We could share this silicon. And we could have oxygens coming off of this. But take a look at this. This is kind of the important part right now. So you got this tetrahedron right here, right? Silicon, 1, 2, 3, 4 oxygen. But you're sharing this oxygen, right? It's being shared with this tetrahedron, but also this tetrahedron. Well, when that happens, you have to share the charges. So what happens is one of the -1s goes with that tetrahedron, and the other -1, because remember this is -2, gets put with that one. It has to share its charge. So -2, but it's being shared with two different molecules. So this one gets shared, right? Got a -1 with this molecule, and you get a -1 with that molecule. Same thing here, -1 shared with this molecule, -1 shared with that one, and I could do that as well, right? If I share each oxygen, what's the charge then? Got a +4, right? -1 goes with this, right? -1 goes with that, -1 goes with that, -1 goes with that. Charge balanced? Does it need to attract any cations? Are these bonds really strong? This is actually one of your more common minerals. SiO2, it's really 4 surrounding it, right? But remember, each one is getting shared. So essentially, get half an oxygen there, half an oxygen there, 4 times SiO2. That's quartz. What did we say quartz was in terms of a mineral property?
Really strong.
Really strong, right? Because all these bonds are strong. It melts at 700 degrees centigrade. You need a lot of heat to break these bonds. Is this going to break easy? No, quartz doesn't break easy at all. That's why quartz is so inert. It doesn't want to react with anything because of all these strong bonds, and it doesn't want any other elements there. It's just happy being nice and pure. It's pure silicon. Si and oxygen combined together is something that we call silicon. So does that make sense? So you can either attract cations, or you can share the corners of the tetrahedron. Sometimes we share all of them like we do in quartz. Sometimes you might only share one corner. That's when you get a chain. Sometimes you might share 2 corners. Double chain, sometimes 3 corners. Get a sheet. All of them have different properties. That's why we have so many different minerals and so many different mineral properties. So I'm going to ask you about this next month when we have a test. So if you don't completely understand this, review your notes, come see me before or after class or during office hours, and I'd be happy to walk you through this again. And the big point that we're now going to use and move forward with is that because silicon and oxygen are so abundant, and because they can form so many different combinations with different cations, with different methods of polymerizing, that we get lots of different varied minerals that are really common. And they're the most abundant group of minerals on the Earth, Moon, Mars, Venus, Mercury, our inner rocky planets. Okay, any questions? You guys are pretty quiet. I don't know if this is advanced for you or stuff that comes pretty easy given your chemistry background that you bring to class. But if it's something that's completely new to you and it just isn't quite sinking in, come by. I'll help you by taking you through this again, and I can explain it different ways as well. So sometimes they're also referred to the rock-forming minerals just because there's so many of them. Okay. Some really common silicates. We talked about quartz. Little picture of quartz there on the right. People always ask me, is that cut that way? No. They'll form that way in nature. They'll form these nice little crystalline shapes if they have open space to grow into, and if they grow really slowly. Feldspars are a group that I'm sure you probably heard even before class today. There's lots of different feldspars. One of the more common ones is called potassium feldspar. It's got the element potassium in it. If you look at this piece of granite up here, this pink mineral is potassium feldspar. Really common. Olivine. Come up after class, this sort of pea green mineral feels really sandy. Each little mineral grain is really small. If you get a big one, you can sell it as a peridot gemstone. But again, it's the most common and most abundant mineral in the Earth's mantle. 2 irons with a tetrahedron, repeat that 1 billion times and you get one of those little green crystals. The micas, there's many different micas actually, and they all have slight differences in chemistry. There's one mineral called muscovite. It's kind of a white mica. Biotite, kind of a black mica. Chlorite has chlorine in it. It's kind of a green mica. Lepidolite, all sorts of different ones. It's kind of a purplish color. Each one has slightly different color and properties because it has a slightly different chemistry. And then the clays. Again, most people don't consider clays as something they think about when they think about minerals, but clays are minerals. You know, kitty litter, makeup, drilling mud. One thing we're going to do today in lab is you're going to start kind of a semester-long project looking at an area of land and whether it's suitable for building or development. You're going to make those determinations. One thing that you don't want to do is build on clay. What would be one of the problems with building on clay?
The ground would expand when it rains and break any of your floors.
Oh, I used to live in a place in South Dakota that had one of these very expansive clays. Some of them can suck up 10 times their body weight in water. And when they do that, they expand. And if you put your basement into one of those and it gets wet and that clay starts expanding, it can crack your foundation. What happens when it dries out? And it shrinks. So you basically put your foundation into something that's doing this every time it gets wet and dry. That's a bad idea. You go look at homes in this area and the basements are bowed in, cracked, water leaks in. It's just, and the other thing too is that when they get really wet, they also get really weak. So if they're sitting on a hill slope and you put a bunch of water in them, they actually start losing their strength and creeping downhill. And some people's homes have simply slid off the side of the hill because they built in clay. And that's one thing you're going to start looking for is, what are the soils in my area? Is this an appropriate soil to build on? So it's some of the things that we'll do over the next few months, and we're going to start actually in lab today doing that. So this is something that you'll take from lecture and consider in your lab. place. So if you have the high demand item like iron, gold, you don't have to have it super concentrated to make a profit. But if you have something like mercury that nobody wants anymore, you basically have to have mercury crawl out of the ground on its own and jump into a bottle so that you can sell it and make money, because any time you put into it, it's just not going to be worth it. And the expense to get it out of the ground isn't going to be worth it. No demand for it. Nobody's going to pay you for it. So again, it has to be highly concentrated so that you basically have to have no expense in extracting and selling it. Something like gold, it could be 0.02 ounces per ton of rock and you can make money on it. Does that make sense? Okay, and then this is about as basic economics as you can get. This isn't an economics class by any stretch of the imagination. But what is an ore deposit? Something that you can make money on in today's economy. So its definition is economic in nature. So even as a geologist, even as a scientist, we are not immune from economics and politics. In fact, those two things drive our industry as much as anything. You look at hiring trends in geology, last few years, oh my gosh. Bachelor's level geologists would start at over $100,000 a year. And that's because the mining industry was buying them up as quick as they could. Now, it's been tougher times in the oil industry. Russia and the Middle East started producing oil at a rapid rate back in early 2015. They flooded the market with oil. What happens when you have a huge supply? What happens to price? It drops. Yeah, Russia came on hard times. Its ruble, its currency got devalued so much. So if your money isn't worth much, how do you get wealthy? You have to have a lot of money, right? So they decided that in order to keep their level of prosperity, that they had to step up their production of oil, sell more of it, so that they bring in more money. It's not worth as much these days, but it's the only way they can keep up. And they have way more in terms of oil resources than we do here in the United States. Middle East did the same thing. So it drove the price down. You guys probably remember just 2 years ago, gasoline was $4 a gallon. It's half that today. It's the Russians and the Middle East. Nothing to do with anything that's going on here. So there's a huge effect between prices and what goes on in our industry. Now geologists are getting laid off. They're the first ones to get hired and they're the first ones to get laid off. So if you're a geologist and you just got kicked out of the oil patch, you start looking for a new job. So there's lots of geologists looking for jobs. Now we're really cheap. Not making $100,000 to start now, but still making a pretty good living. So a lot of them are going into areas like hydrology, environmental geology, different kinds of mining. So again, back in the 1980s, copper was important. We used it in wires. And then somebody came along with a better idea. Demand for copper dropped. Prices for copper dropped. Well, as it turns out, back in the late 1990s, they started finding more uses for copper. Demand goes up. What happens to price? Price goes up. In the meantime, during the 1990s when copper was low, there were a lot of new inventions in the mining industry that allowed them to do it cheaper. So when you have prices go up combined with your cost of getting out of the ground going down, what does that do to your profitability? It increases. Now mines are opening again. And that's just the cycle with Earth resources. It's boom and it's bust, boom and bust. I've lived through 3 oil booms during my lifetime. And now we're going into my third oil bust during my lifetime. All has to do with supply and demand. All right, this is a new section, and I don't want to do it right now. It's more than 10 minutes long, so what I will do though, okay, so we can meet for lab at 12:30 again. Today is kind of a play day, okay? We're going to start a group. You can do it as an individual too, or you can do groups of anywhere from 2 to 5. And you're going to pick a 4 square mile real section of land around Greeley, and you're going to study it the rest of the semester. And you're going to determine whether it's good to build on it, sucky to build on it, whether it holds resources that could be exploited. If you own those 4 square miles, what would you do with it? And to figure that out, you're going to look at the geology, you're going to look at the rocks, you're going to look at the soils, you're going to look at the water, you're going to look at how it's used now. You're going to see if there's anything on that land that you can make money on. So today, you are going to play around on the computer and find different data sets that will tell you about that land. You'll be able to look at Google Earth, and then at some point I want you to actually go out and look at it. Take a drive, take your bike, whatever, head out there and take a look what's out there. One thing you never do, even though it's a class project, you don't go walking around on people's property, okay? You get shot, that one's on you. That's not on me. So don't walk on people's property. Use the roadways, use trails, you can see what's going on. You don't have to go and bother some farmer's pigs or something. So just be good citizens. If you really, really want to check something out, ask the landowner for permission. That's cool too. So we're going to do that at 12:30. So I have your lab. It kind of details it, and we'll talk through it then. But 12:30, and we can meet down in the computer lab. Okay? So see you in an hour and a half or so. If you want to pick up the lab early and look at it, it's up here, but completely not necessary.